All right. Today we're going to talk about force and about why mass matters. And maybe you recall the joke. I said line up and I'll drop a marble on your toe for an A, or I'll drop a bowling ball on your toe for an A. And one of them you're willing to do and one you shouldn't be willing to do. Because mass matters. Because a marble only weighs about 10 grams. Bowling ball probably weighs about 6 kilograms or 6,000 grams. And the mass difference matters because if I drop that, say, 1 meter onto your toe, we bring out your toe here, all right? And we're going to drop the bowling ball 1 meter. And we're going to drop the bowling ball right on your foot. Bam. We know that's going to hurt way worse than dropping the marble. Why is that? That is because mass matters. Do they fall at the same speed? Yeah, they fall at the same speed because speed is not dictated by mass. So if I want to figure out how fast they fall, I can use my equation here. Vf squared equals Vi squared plus 2As. I can input the acceleration, which is gravity, the distance, which is a meter, and I can calculate that the velocity of the marble and the bowling ball is 4.4 meters per second. Both of those would hit your foot at that speed. But we all know the bowling ball hurts and the marble doesn't because mass matters. And we have to give that a name. They hit our foots at 4.4, but the product of mass and velocity is what dictates force. And we call that momentum. Momentum is what dictates force. And it's a combination of the mass of the object and the velocity of the object. And recall, velocity is a vector. It has a speed and direction. When I drop the bowling ball, it's going 4.4 meters per second down. Thus, the momentum will be down also, crushing your big foot and knocking off the red toenail polish. All right, so let's talk about it. The bowling ball's momentum in this case would be 6 kilograms times 4.4 meters per second down. And if we do the math here, and I'll grab my calculator, 4.4 times 6, I get the momentum is 26.4 kilograms per meter second down. So that hurts. We know that because we can picture dropping a bowling ball in our foot. The momentum of the marble doesn't hurt.
I'm going to put these in your area.
Okay. Everybody silent, Miss Elmer. All right, so now, as we do this, I multiply this out, and I get 4.4 times 0.01. I get the momentum of the marble is only 0.044 kilograms per meter second down. Low momentum, high momentum. But the way we have to do this now is to consider what force is. And force is how much momentum you have over a change in time. Force is the change in momentum over the change in time. And again, momentum is denoted with the letter P. So little p, which is probably, again, a vector quantity, so force is a vector quantity, is equal to the change in momentum over the change in time. But we know momentum is mass times velocity. And we know that typically we do not change mass. Rocket ships change mass. When you burn a rocket, the oxygen, which is usually the fuel, burns. The mass can be going down. But in most cases, what we do on Earth, the mass stays constant. So we can pull that outside of the delta and put it out in front. Now, we also know that the change in velocity over the change in time is acceleration. And thus, Newton's second law, force equals mass times acceleration. Again, it's a change in momentum and a change in time. We won't do it this way very often. We will almost always do it this way. But we need this formula right here with the red asterisk because we want to talk about impulse. All right? V is linear momentum. It's what does it. Impulse really is the momentum change in time. So it's a change in momentum for a given time. Momentum change is shown here. Change in momentum is equal to delta mv. But again, we don't change mass. We're not burning rocket ships. We're dropping marbles. All right? If I bring the mass out again, and I know that I can write this here as m delta v for delta p, I can solve for the impulse or the change in momentum by bringing delta t over. So anytime you have a force times a change in time, that'll be equal to this. Well, this is the change in momentum. Again, you guys always want to know what to put in your formula sheets. Your formula sheets are fairly easy. You have momentum, all right, which is a vector quantity, which is mass times velocity. You're going to have impulse, which is delta p, the change in momentum, which is going to be the force average times delta t. And finally, we have the equation from Newton's second law, which is force equals ma, mass times acceleration. These are the three equations you need to do problems. We already calculated the momentum of a bowling ball and a marble. We probably could do something with impulse and say something like a rocket fires its engine, say at 4,000 newtons force down. Now let's say that rocket burns for 40 seconds. The question is, what is the impulse? Well, the impulse here again is delta p. That'll be the force average times delta t. It is 4,000 newtons times 40 seconds. I get 160,000 newton seconds. Again, these take a little practice. Look at the examples in your book on impulse and momentum change in Chapter 4, about page 101 through 103. The homework problems are basically the same as these.